Yeah, so I will be talking about the ROSPlan for the next hour. So the plan is to divide this into 3 sections. So the first one is ROS. The second one is ROSPlan, and the third one is just questions and answers. But I mean, if someone has a question in the middle, I'm okay with the interruption. It's fine. Or you can just write it in the chat, maybe. Yeah. So let's start with ROS. So what is ROS? So ROS stands for Road Operating System, and it's not really an operating system per se, but it's, let's say, easier to explain to people like that. But a more comprehensive definition of ROS given by the CEO of the Open Source Robotics Foundation, which is Brian Gerke, is that ROS is a combination of A plus B plus C plus D. So let's go with what are these letters. So A is the plumbing. Plumbing here refers to the let's say all the code for providing you with a published subscription infrastructure, so that you can create easily these components that will communicate with each other through throughout the system. But yeah, we will see the details later. So it provides with all the plumbing. So the second one is the tools. So ROS also provides with an extensive set of tools for configuration, for introspection, for debugging, visualizing, logging your data, testing and deploying all of your code into the real or simulated robots, right? In a distributed computing system. So distributed here means that there could be multiple processes running on different computers, and they will just seamlessly, you'll be able to communicate with each other through the network without having to implement that part yourself. And then the C is the capability. So there is a broad collection of libraries that implement some high-level robot functionality. So for navigation, manipulation, perception, and yeah. So that's the main focus of the libraries provided, but there are many others. I mean, ROS is open source, so there are contributors all around the world increasing these libraries constantly. And then the last one is the ecosystem. So the ecosystem is actually very important because this means that there is a community of people all around the world using ROS. And so there are questions and answers forums with an extensive set of questions. Like I mean, last time I saw there were like more than 45,000 questions there. So we have an extensive wiki at ros.org. So if you have questions on how to do a particular stuff, you can go there and benefit from this community-supported wiki. And of course, I mean, if someone has an issue or something does not work, also some repositories are also maintained by the community. So this is what is ROS. Now we'll go through 5 different basic concepts in ROS. So basic concept number 1 is a node. So what is a ROS node? Is a process that performs some computation. So the code is organized in small nodes that are multiple processes that run in your computer. They are combined into a graph and they communicate each other using topics, services, action lib, and the parameter server. So, like I said before, nodes can reside in different machines, and the user does not need to worry about that. As long as those computers are in the same network and they can ping each other, then ROS takes care of the rest. Yeah, so the basic concept number 2, which is a topic. So what is a topic? A topic is a bus. So in this case, the topic is depicted in the picture as a pipe. So the pipe is the bus, the channel from which the message is going to be transmitted between the nodes. And the message here is depicted by water, but it's more like small packages of information. So each of these messages will go through, or will travel through these topics. And so we have this design pattern, which is based upon a producer and a consumer. So a node will produce data or will publish data to a topic. And later on, another node will subscribe to this data and will consume. Yeah, so nodes that are interested in data, they subscribe to the relevant topic, and nodes that are that can produce meaningful data that could be published to the network, they will do so through topics. Yeah, so some properties of topics is there could be actually multiple publishers and multiple subscribers to a topic. So this is one property. So it's unintended for unidirectional. So let's say if I'm publishing a topic, I cannot, well, yeah, I could subscribe, but maybe it wouldn't make much sense to do that. It's intended for streaming. So if you want to publish multiple messages to a particular topic, then this is what the streaming is about. So a constant flow of messages is the intention of these topics, and the nodes will communicate with each other by publishing messages in this topic. Yeah, sorry. The last point is that the messages have a type. So you have basic types like integer, string, and float, and so on. But these basic types can be organized into some meta types, let's say. And each of these messages can hold some internal structure of a combination of one integer, one string, and one array of point clouds or some other more complex types. And then the third basic concept is the messages. So you already saw intuitively what is message here. We already talked about it, but here, I mean, imagine you are in your house and you want to send a package to someone. So the truck would be like the topic, and the message would be like the envelope. So you can send continuously like multiple messages to the final destination. And yeah, so a message will just state what kind of information your node needs to produce. So does your node need to produce, like I said, a combination of an integer and a string, or maybe everything that you need is just a string to communicate the strings with the topics, through the topics, or maybe some more complex thing like an image or laser scanner data or something like that. Then the basic concept number 4 is the service. So service is a client-server communication pattern. And so the thing is that you will have on one side, you will have the client, on the other side, you will have the server, and then the client will make a request to the server. Keep in mind that the client and the server here can be on the same machine or can be on different machines, depends on how many machines you have on your system. But I think for the purpose of this course, you will do everything on one machine. So just keep in mind that here the client and the server will be on the same machine. So there will be two different nodes communicating with these through services. And then what you will do is you will send a request with some data or parameters for the request, and then you will receive a response from the server. with feedback only one time at the end of the process. So once the server is finished with what you ask him to do, it will send a result one time at the end. And it's typically a blocking operation, but you can also specify a timeout, or you can make a non-blocking operation. But typically you will send your request and then wait for the response from the server. So this will block your process, and then you will receive the response once the server is done with your request. So these services are very much used in ROSPlan, so that's why they are important. So the basic concept number 5 is the action lib. So action lib is actually very, very similar to the services. So you also have like a client-server architecture. The only difference between services and action lib is that you can do a bit more stuff with action lib. So you have more control over the process. So the first one is that the first difference is that in action lib, you can get periodic feedback about what is going on with the request. So if the request that you made takes a long time to process, you might want to get some feedback in the middle. So to know what is the progress, what is going on, and maybe some data structure with some messages saying, giving you some visual feedback about what's going on with the request. The next difference is that you can have the possibility to interrupt the task, so preempt. So you can preempt the task, and then later on you can resume the task, or you can cancel the request. So you see that you have a little bit more control with action lib. And action lib is something that you will use to wrap the skills of your robot that are ultimately these the planning actions. Yeah, a little bit of the development in ROS. So mainly there is support for C++ and Python, but there is also experimental support for multiple other languages. So you have a wide variety of languages. So for example, you have you can write your nodes in Java, in Lisp, in Node.js for web development. You can use Lua, Ruby, R, Go, and many more. So there is experimental support for all of these languages. So the code, so these nodes, I mean, we talked about the nodes, but we didn't talk about the packages. So the nodes will be organized inside ROS packages, and the ROS packages will live inside what is called the Catkin workspace. So Catkin comes from the name of from the flower. So I put here an image of the Catkin flower, and you can see here like it's some sort of like a tree structure. And this Catkin workspace is like how you will organize your code. So you have the nodes, you have the packages, and you can have multiple packages that all live inside the Catkin workspace. And what is a Catkin workspace? Catkin workspace is just a folder where you modify, build, and install your ROS packages. So next we will talk about ROSBash. So ROSBash is just a collection of commands and alias and autocompletion. And to give you some examples, so you have ROSCD, ROSED, ROSCAT, and ROSRun. So ROSCD is just an easy way to navigate to your package. So you will do ROSCD from the command line, and you can start typing the name of your package, press tab, do the autocompletion, and then you don't need to type the full path of your ROS package. So you can just from anywhere in your directory tree, do ROSCD package name, and it will take you directly there. So these are tools that are very useful. And another tool is ROSED, package name, file name. So if you want to quickly edit a file, a launch file, a Python file, or a C++ file, any type of file, so you can just do ROSED, the name of your package and the name of your file that you want to edit, and then it will pop out in your favorite text editor. So this is to quickly edit a file. ROSCAD is similar to ROSED, but instead of editing the file, you will just print it on the console, on the terminal. And then finally, I mean, there are many more commands from ROSPash. I'm just putting here a few, but the most important ones, maybe the next one would be ROSRun, package name and the name of your executable. So when you do this, you are launching a process. And if it is a Python process, you need to ensure that your Python file is in executable. So you do this by doing chmod plus x, then the name of your file, and then your file becomes executable, and then it will be recognized by ROSRun. So this is important for Python files. And if you have C++ files, you need to make sure that you have compiled them earlier with catkin build or catkin make. And this binary will get created under your devel folder, which is a part of your catkin. And then once you have produced the binary, then you can use ROSRun, the package name, and then the name of the binary to run that process. So next, I will like to talk about 4 important libraries in ROS. So the first one is TF. So TF it stands for Transformation Library. So in robotics, you have, of course, multiple coordinate frames, which are part of the robot. And maybe also not part of the robot, but if the robot is perceiving an object and this object gets, you get the detection of what this object is and where it is with respect to the camera. So you will likely attach a frame to that object. And because you know the transformation between the camera and the object, then you can just make a transformation and know the relative position of the object with respect to the arm, for example, so that you can pick it. So this transformation library will perform this computation for you, and you can transform points, vectors, point clouds, and many more things, laser scanners, data, between any 2 coordinate frames that belong to the same transformation tree. So the next important library is MoveBase. So MoveBase is for the ROS navigation stack. And the ROS navigation stack provides you with the high-level functionality to move your robot from between 2 locations. So this is a bunch of things that are happening in the background for you automatically for you when you call MoveBase. And one of them is the localization algorithm, which is here handled by the particle filter. So this is the robotics algorithm that tries to match the laser scanners of the robot with a known map. And then you can know the XY position of the robot in the environment. And at the same time, you have the processing of the laser scanner readings, which is here. So you have different sensor sources. So you might have a laser scanner, you might have a depth camera. And with those sensors, you are perceiving the world and you are maintaining a local cost map. So the local cost map is what you see here in purple. And this is basically the obstacles. So how the robot will perceive the obstacles. And based on that, you will perform a global planner. The global planner is here depicted in blue. And this is like a high-level plan of where the robot needs to go in order not to collide with the obstacles. And then a local planner will try to follow the global planner incrementally so that it makes small steps towards the final destination. So what you need to do is you input a pose where you want the robot to go. You call move base and you say, okay, robot, go there. And robot will take care of the rest for you. Another important library which is there in ROS is MoveIt. So MoveIt is a manipulation framework. So this will allow you to move the arm. So if you have your robotic arm and you have a description of your environment, which is here depicted in blue blocks. So these blue blocks are obstacles that the arm needs to avoid, not to collide with them. And then you have an initial arm configuration and a final arm configuration. So then MoveIt will search possible configurations that will move the arm from the initial configuration to the final configuration with some constraints, like maybe you want the robot to go like fast or speed, or maybe you want the end effector to maintain a particular orientation. So for instance, if you are moving a glass of water from point A to point B, you don't want to spill the water. So you want to add a constraint so that the end effector is always pointing up and stuff like that. So again, like in MoveBase, you have like a big architecture with lots of nodes that are communicating with each other to make this possible, so that the arm can move between different configurations. And then the last one that I would like to talk about, I mean, there are many more, but these are the most important ones, let's say. It's RVIS. So RVIS stands for Robot Visualization Tool. And what RVIS is, it's a GUI interface that allows you to visualize what is going on inside the robot. So sensor data and debugging data that also sometimes you want to produce, like a marker, for instance. So you could actually draw things on this GUI. So you can draw, I don't know, a box, you can draw a line, you can draw points. And you can there visualize the sensor data that is coming from your robot. So you will have there the possibility to visualize sensors, laser scanner data. For instance, just to put you an example, a laser scanner is just an array of distances. And sometimes you have as much as 550 of these values at a frequency of I don't know, 30 hertz. So this means that 30 times per second you are receiving a message with 550 distances. So of course, I mean, for us humans, it's impossible to be able to make sense out of this data. So what we do is we do a 3D representation of this data with nice drawings, and then we put it into RVIS, and then we can see what's going on in the world. So this is also very, very nice tool. Yeah. So with that, we are finished with the ROS part. And if someone wants to ask a question, then you can interrupt here or at the end. If not, then I proceed with the ROSPlan part. Okay, I will proceed then. Oh, a question. Are there alternatives to ROS? Yes, of course, there are many. So you have, I think I heard about all other robot middlewares such as YARP. Here at the FKI, we actually have our own middleware, which is called ROC. You have also Orocos from KDL University. No, sorry, it's from Leuven University in Belgium. And many more. I mean, there are, I think, like more than 15 or so but ROS is the more popular one, the more strong one in my opinion. It's not perfect. I mean, you also have some problems in ROS, which the community is trying to fix, and therefore, I mean, here in this talk, I'm mainly talking about ROS1 and addressing ROS1, but a second version of ROS is already on its way. It's there since 4 years now, and it's getting more mature, and very soon it will be actually time to migrate to this ROS2 version, which addresses many problems that the community has experienced in the last years, and tries to fix those, right? Yeah, so another question, in what cases we want to use client-server messaging instead of using topics? Yes, actually, I mean, the client-server architecture, so these are ROS services and ActionLib. Under the hood, they're actually using topics. So the thing is that if you want to request a service from a node, you could implement your own service just using topics. So you make one topic with the message, with the parameters that the service requires to work, and then you publish this message on a topic, and then you will need to implement some sort of like a while loop to wait for the message from the response to come from the node, so that you block the process, right? And then on the server side, you can just implement a subscriber for a topic, and then you do the computation of the service, and then you publish a result message at the end. So you see that already just to create a service, you need to make 3 message types, and you need to do this manually. So the service is just like an easy way of doing all of these things, and to save you some time in not having to create these messages yourself. So in principle, you could do everything with topics, but with services, it's just faster. Yeah. So let's go to the ROSPlan part. Yeah. So what is ROSPlan? So ROSPlan, it's a framework that provides a generic method for task planning in a ROS system. So this is just taken from the GitHub repo. And intuitively, I mean, ROSPlan are the first steps towards the integration of AI planning and robotics. So, I mean, we do not claim to have like a full solution because it's a hard problem, but we are continuously working there to improve and to make it better. So it uses different technologies to provide with a high-level robot control. And so, I mean, there are multiple ways of that you can control the skills of your robot. So you could use state machines, or you could use behavior trees, or Petri nets, or some reinforcement learning technique if you want, or something like that. And ROSPlan provides you with an alternative to do your decision making using planning, task planning. And so what is currently supported by ROSPlan is mainly PDDL 2.1, but we also have experimental support for probabilistic PDDL. We have this integration with Riddle, made by Gerard, and it's we also have support for hierarchical task networks, but this is coming. So this is work under progress, and we will talk a little bit more in depth about this HCN integration on a lecture on Thursday. Yeah. So also part of ROSPlan is plan execution and monitoring. So you have 2 ways of doing this. So either you do the simple plan dispatch, which is a sequential action dispatch mechanism, or you have a more complete, more smart way to dispatch your plan, which is the serial plan dispatch, which we will talk a bit later, more in depth. So this is the architecture of ROSPlan. So you have five main nodes. So Gerard, yeah, sorry. So there is another way to dispatch plans. Yeah, so this will be the dispatch for probabilistic planners. Yeah, if you use Riddle, then you have to use this dispatcher, of course, for dispatching probabilistic actions. Yeah. So the general architecture of ROSPlan, you have five nodes. So one node is the knowledge base. So this will store the model, the PDL model, or the RDDL model, or the HDDL model, and also the current state of the world, the symbolic state of the world. So it's storing all your predicates and the goals and the instances. And then you also have the problem interface. The problem interface queries the current state from the knowledge base, and it creates a problem instance. So this will be like a problem.pddl file. And then assuming that the domain is fixed and the problem has been just generated from sensor data, because the knowledge base gets populated with sensor data coming from the robot. And then the planner will, the planner interface is just a wrapper for an AI planner. So inside here, you will have your FF planner or your POPF or the planner that you make maybe. And it will produce a solution. And then this solution will be, needs to be parsed. So because this solution is just a text coming from the terminal, and you need to somehow process this text to know if the plan was successful or it was not successful, and to be able to extract from this big string the actions and the parameters of the actions and the dispatch time and the duration of the actions. So this is what the parsing interface is doing. And if you're using the sterile plan dispatch, then the plan will actually get converted into a graph representation. And this graph representation will finally, using some rules, you can just go through the graph and dispatch the actions to the robot finally. So this is just like a general overview, but we will go a bit more in detail with some of these components. So yeah, like I said, knowledge base. So first of all, stores the symbolic planning model and the current state of the world. The way you communicate with the knowledge base is via services. So you do raw service call, and then the knowledge base and what kind of information you want to put there, or what kind of information you want to delete from there. And then knowledge base will handle this database for you, and it will add or delete your facts or your goals or your instances. The next component is the problem interface. So like I said, you query knowledge base snapshot and you create a problem. Yeah, so this would be like a PDL.problem that will ultimately feed the planner. And then the planner interface is a wrapper around your AI planner, and you will write the output of this planner to a topic as a big string. And then the parsing interface will convert that big string into representation which is suitable for execution. It can be either like a sequential plan dispatch or the sterile one. And finally, the plan dispatch will handle the execution and monitoring of your plan. And we also have some debugging tools in ROSPlan. So we have two GUIs. So the first one is a GUI to visualize the knowledge base, and it also allows you to manipulate the knowledge base. So because typing service calls from terminal can be slightly more complex than doing it with the GUI, of course. I mean, GUI, you press a button and the knowledge is there. So the knowledge base, the RQT GUI can also delete facts or goals from the knowledge base, or you can also add goals or add facts or instances to the knowledge base using the GUI. And so what the GUI will do under the hood is a service call, but that is transparent for the user if you do it with the GUI. And the second GUI is the sterile RQT. And the sterile RQT allows you to visualize the graph and the plan that has been converted into a graph representation. And here you also get some feedback about what's going on in real time. So if the node is in green color, this means that the action has been dispatched and the feedback has been received. So this action is completed. If the node is in yellow color, this means that the action has been dispatched. So it has been sent to the robot for execution, but you are still waiting for this action to complete. And if the node is white, this means that you have done, you're not done with this action. You haven't sent for execution and you haven't received anything, of course. So you need to wait until you receive the feedback from this action to be able to activate this one. So you can track the progress of your plan with this RQT. That's what I'm trying to explain. Yes. So just to give you a little bit more detail about the knowledge base GUI. So in this part of the GUI, you will have the execution status. So which actions are dispatched and what is their duration and status. So either they are complete or just dispatch and so on. And in the next part of the RQT, you will have the goals. So these are the unfinished goals that the system is trying to accomplish at this particular moment. Next one, you have the collection of the facts. So these are all the facts in the world, assuming closed world assumption, and then ultimately you have the instances and their meta types here. Yeah. So the next one in ROSPlan, the next component is the action interface. So ROSPlan provides with a base class implementation to facilitate the process of creating an action for your robot. So let's say for execution, if you want to execute the actions that are inside your model, so what you need to do is inherit from this base class, which is the RP action interface class. And then once you inherit from there, you implement a virtual method, which is there with the concrete implementation of what you want your robot to do. And then this action interface will do some things for you automatically. So what it will do for you is first, it will subscribe to the plan. And if the action is relevant, then it will proceed. If not, then it will exit and do nothing. Next, it will automatically handle the action lib feedback for you. So you don't need to code this part in action lib. And it will basically tell action lib feedback that the action is enabled. And then the next one is your concrete implementation. So here is where you need to override this or implement this virtual function to actually do what the action, what you want your robot to do. So this will be navigate to somewhere, or move the arm to somewhere, or trigger your perception algorithm so that you perceive an object, and so on. And once you're done with your concrete implementation, then the action interface, if inside your function in your step number 4, if you return true, if this concrete implementation function returns true, then this means that the action has succeeded. And if the action is succeeded, then this interface will update the knowledge base automatically for you based on your model. So this means that it will apply the effects of your action. So the add list and the delete list, and it will update the knowledge base accordingly to the add and to the delete list. And then the final step is to handle the action lib result, saying that the action has been achieved or that the action has failed. Yeah, so the next tool that we have in ROSPlan is the simulated actions. So this is the RP simulated action interface. And what this is I mean, sometimes while you are developing your solution, maybe you don't have a simulator like Gazebo or Stage or VREF or so on. And you just want to test the planning part, let's say. So you want to mock up the robot and you want to fake the robot just to see that your pipeline is running properly. So for this, we have a synthetic simulator of actions. And this made as a replacement of a physics-based simulator, which would be, like I said, Gazebo or PyBullet or Stage. And it will just fake the actions, and it's useful for testing and for debugging. And you have 3 parameters here, which is you can specify the action duration with some standard deviation. And you can also specify a probability of success of that action. And if you are using a deterministic model, you can just set the action probability to 1, and then action will always succeed. Or if you are using probabilistic model, then you can set the action probability to whatever you want, 0.5, 0.7, and then half of the time the action will succeed and half of the time it will just fail. So under the hood, this is just using a random seed and setting some random value there for you, either true or false. And next in line, we have the sterile plan dispatch. So we talk a little bit about the sterile plan dispatch, but here we will go a bit more in depth. So what the sterile plan dispatch is? So it's a real-time graph-based algorithm for execution and monitoring of your plan. And one property of the sterile plan dispatch is that supports concurrent action dispatch. So this is useful, for example, in a multi-robot scenario where you want both robots to do something at the same time. Or even the same robot, it can do multiple actions at the same time. So for example, it can maybe slightly move the arm in some direction while it's navigating at the same time. If you are sure that this is safe to do, then of course you can do it. And so one of the features of the sterile plan dispatch is that preconditions are checked during runtime. So before you send an action, sterile will check for the preconditions automatically for you to ensure that the action is ready to be executed. So this might seem trivial, but it's actually a lot of steps. So you need to query the knowledge base to get the operators, and then you need to fetch the preconditions, and then you need to compare the current state of the knowledge base and match these two. And the Steril does that for you. And so the Steril plan dispatch in a nutshell. So it converts a temporal PDDL planner output into a graph representation, and in the graph, the edges represent ordering constraints. And then later on, you will send this graph for execution. Yeah, so because we have a feature so that you can enable colors in the Steril graph, so it's important also to talk about the semantic behind the edges. So what are the meaning of these edges? And so we have conditional edges, we have start and end action edges, and we have interference edges. And here the green edges are conditional support edges. And they what they mean, I mean, there are causal links. So there are action and effect in your actions. And here you only see one edge, but it encapsulates all of the causal links. So there could be one or more causal links in this encapsulated inside the one edge. And then basically all of the edges, it doesn't matter if it's conditional edge or if it's start end action edge or interference edge, all of the edges, they represent ordering constraints. So this means that unless the node has received all incoming edges, it cannot fire the action. So in this case, for A1 to start and to fire, first it needs to wait until A2, sorry, until A2 has been dispatched and A2 feedback has been received, and then A1 is ready to fire. So edges are ordering constraints. And yeah, like I said, nodes cannot fire unless it has received all incoming edges or signals. And yeah, so this is just how the Steril is generated. So this is the input for the Steril plan dispatch, which is how the planner will produce the output. So this is the POP-F output. So if your domain is a temporal domain, then you have here some information. So this is telling you the time, the dispatch time. So this is dispatch this action at this time and expect this action to have this duration. So what you will do is you will split these actions into two nodes. So one for starting the action, one for waiting for the feedback. And then in this case, we have two actions here on our plan. So we will have 4 nodes. And of course, we will create a dummy node at the start just to have initial point where the initial state can be connected to the actions. And then once you have the nodes, because we have splitted the nodes ourselves, so we know which is the node that starts and which is the node that ends, we can create one edge between them, which is this edge in red. That is the edge of start and end action. And then later on, we will add the causal links. And the last step is to add the interference edges. Maybe this is going like too specific, but I will just quickly go through it. So 2 nodes, A and B, interfere if the positive effects of A intersected with the negative effects of B are non-empty. So These are the 4 definitions of interference, and ROSPlan is checking only the ones marked here with the star. And this will be an example of how this interference could happen. So this is mainly when a node is destroying the precondition that is required for another node to be activated. So this means that in order for this node to start, you first need to start this node. Otherwise, this precondition will be destroyed, and then the preconditions for this node will not be met. So just to finish with the sterile, I mean, what this means is that even if the output of your planner is sequential, here you can smartly identify actions which can be executed in parallel. So this is one nice property of the sterile. So it sort of reconstructs a little bit the search graph and smartly tries to dispatch the actions. And we are coming to the end. The last 2 things that I have is just to make you aware that there are some demos that are available in ROSPlan. So here we have some of the demos. So you have an example of how to launch the stage simulator. You have exploration demo in stage. So this connects all of the components in ROSPlan. So you have an example of how to make a PDDL model, how to connect the nodes between each other so that the pipeline can be called one by one. So first the problem generation, then the planner interface, then the parsing interface, and then finally the execution. And another demo that we have there also in ROSPlan is with Gazebo Simulator and Turtlebot 3 and Turtlebot 2. And what this demo will do, it will query the map, it will subscribe to the map and check for feasible waypoints where the robot can go without colliding. And then it will make a plan to visit these waypoints. And then it will just call MoveBase to go through these waypoints one by one so that you are exploring the environment. So this is what this demo is about. And finally, here, I mean, I will share the slides, and if you go to this link, you can see the whole Turtlebot demo that I've just talked about here. So you can see all of the nodes that are part of ROSPlan and what are the input and what are the output that they are producing, so that if you study a little bit this PDF, then you get in one shot, you can see what ROSPlan is about. And with that, I finish my part, and then I open for questions and questions and answers for the audience. Yes. So.
Thanks, Oscar.
Yeah, you're welcome.
So you have a question from Salah asking, how does the ROSPlan workflow look like? Perhaps a personal example.
The ROSPlan workflow, it's basically this thing here. I mean, but this is of course not visible because it's like huge, and the text is just too small. So you will have to open this in your PC, let's say offline, and just go through it like for 15 minutes or so. But here we have the same nodes that are here. We have them also here in this diagram. So the basic workflow is you will first populate the knowledge base with sensor data, and then you will convert your sensor data into facts. So this will be the first step. The second step is you query a snapshot of the current state of the world and you generate a problem. And then after you generate the problem, you call the planner. So to produce a plan. And then after you have produced a plan, you will convert this plan into some representation that is suitable for execution. And then finally, you will just dispatch the actions in the plan to the robot. So this will be the basic workflow, let's say.
I'd also add there that the hands-on material for this lab, which will be disseminated pretty soon, will also include some walkthrough of how to run ROSPlan and to call all these services.
Mm-hmm.
So Oscar, Thibault asks, how do you bind your logical actions to the physical actions? It's a very good question.
How do you bind the logical actions to the physical actions? Yeah, I mean, this is a problem, I think, in robotics mainly. So what you do as a roboticist, I mean, you have to be expert in robotics a little bit, know a little bit of navigation, a little bit of perception, a little bit of manipulation. And this can be quite complex topics on their own. So for example, it took me, I don't know, around 6 months to fully dominate navigation in robotics, maybe another year to dominate manipulation. At least at a conceptual level, you need to be slightly an expert on this, so that you know how to construct your model, right? And then typically the actions in PDDL, or the actions that are part of your model, are high-level actions, simplified actions. But under the hood, you will have to most likely make a state machine that is going through a lot of intermediate steps so that these high-level actions can be called. So what I mean to say about that is that inside MoveBase, there is a state machine that is doing a lot of stuff for you. And inside your move arm action, there's also a state machine that you need to, that you can code, or that is already available for you. And you, as a domain expert, you need to handle what to put in the PDDL model and what to put in the state machine, so that you have this balance. Because in theory, you could put everything on the planning side, but there might be a sequence of actions which are always going to be in that order, and it does not make sense to plan for those actions. So you just need to do a state machines for those. Yeah.
Tianyi asked, for actions, do you have to implement all of the ground actions? So it's a related question.
Yes, I mean, you will have to implement all of your actions, of course, yes. So you have to create one interface per PDDL action. But like I said, I mean, creating these actions is easy because we have provided with a base class to do that. So this is related to this slide here. So you inherit from this base class, and then you make the concrete implementation. And you need one action interface per action in your model.
Fansha asked, what are the main challenges in ROS and ROSPlan that still need to be solved? Salah asks the same question.
Yeah, there are so many, because I mean, the thing is that, so I would say there are challenges for ROSPlan, but there are also challenges for the planning community. And if I mean, ROSPlan inherits the weaknesses of the planning system that you are using. So if you are using PDDL, there will be, of course, a lot of like assumptions that you are making, such that the the action, so the outcome of executing an action of your robot will always succeed. So this is an assumption that PDL makes, and of course this is not the case in reality. You have a stochastic action outcome, you have events. So I'm not sure if events are supported in ROSPlan. Michael, what would you say?
So we didn't talk about events this morning. Are you meaning like PDDL plus events?
Yeah, exactly.
So PDDL plus events model exogenous changes in the environment that don't come from the agent, but are instead triggered by some other consequence. The way that would manifest when executing a plan using ROSPlan would be that the state would change as a result of these events, and because they were encoded in the planning domain, they would not, the plan would not become invalidated by these exogenous changes. So it sort of doesn't really change anything in ROSPlan. You just assume that because your planning domain was a better, more accurate representation of reality, your plan is more robust as a result. That kind of ties in with Anders' question, what if you need to make a new plan because the facts are no longer feasible with the current plan? Oscar, maybe you can explain.
Yeah. So, I mean, in principle, if you give a proper maintenance to your knowledge base, so you will query a knowledge base snapshot, you will create a new problem, and you will just call the planner, and the planner should create another solution for you. The question is maybe if the planner cannot make a solution, so if the plan is not solvable, then I would say the best thing you could do, one thing you could do is just wait until new information, new knowledge arrives, and hope that this new information can make your plan solvable. So this could be one thing. But actually, I mean, in ROSPlan, these nodes are provided to you, but it is also expected from the user of ROSPlan to connect these nodes in multiple orders. So you don't need to connect these nodes in sequence, and you can connect them in any way you like. And from this perspective, also ROSPlan is a nice tool for research, so that you can also like experiment with all of these questions, right? So what I'm trying to say is that it's designed in a modular way so that you can reuse these nodes at your own will. Mm-hmm.
So if Anna asks again, intuitively, what is missing in the current state of the art is the ability to simulate the problem with good precision, or not being scalable because of the large state space.
I think there are so many challenges. I mean, just to name a few, there is also a challenge of explainability. I mean, in robotics, you ask the robot to do something, the robot fails to produce a solution, and at the moment it will just tell nothing. So this is not intuitive for us. And what would be nice to have is if you tell the robot, go and fetch me a bottle of water from the kitchen. I would like the robot to respond to me. I cannot do that because there is no bottle in the kitchen, for instance. And then I would say, okay, but I just went shopping this morning and you didn't realize. So the bottle is there, trust me. then the robot can add this bottle to the knowledge base, and then there's more interaction between the two of them, right? So this explainability it's a challenge for the community, and it's also something that is missing. The other thing is with action failure. So when a robot fails to do something, for instance, PDL has models for success, but it does not have models for failure. So what to do if things don't go according to the plan or to the model? And one thing that you could do, I mean, is just replanning, right? And this typically what we do at the moment, but there could be more interesting ways to recover from those failures. One of them could be maybe to have a failure model, explicit failure model, so you know what to do in case something goes wrong. And these models are there in the literature. I mean, you have them in behavior trees. If you talk about hierarchical task networks, there's something that you could do without replanning, actually. So you could just go up in the hierarchy and try new solutions. And so this is also a big problem in robotics. The other problem is with the sensor data. So sensor data, it's faulty, of course, and the sensors are lying to you, and this means that the predicates, the facts that you are making from that sensor data, it's also, they have a probability of being true, and is not 1.0 in robotics is not the case. So the fact that the robot is in the kitchen has some probability of success. A probability of being true. And usually these facts, this information in your knowledge base they are not independent random variables. Sometimes there are dependencies between them, and there is a correlation between those facts. And what you have here is basically like a network of facts, of probabilities, which are dependent to each other, right? So this is also a challenge that we need to address. And these are just a few examples, but there is still a lot of work ahead if you want to smartly execute and combine these two worlds, right? AI planning and robotics is some of the things that come to my mind right now.
So we have a few more questions here. Thibault asks if there's any standard way for defining the correspondence between location 1 in the logical world to XYZ and quaternion in the physical world.
Okay. Yeah, that's a very good question. I mean, this is actually related to environment representation, and environment representation can be initially naively thought as something easy and simple, but it's actually very, very complex, and it's I would say even another research area. So here at IFKI, we have persons working full-time in this topic, which is environment representation, and they are dealing with this conversion of sensor data to symbols, and also the other way around, converting the symbols to the sub-symbolic information, which is in this case the pose that you mentioned. And I mean, if your research area is not environment representation and you just want a quick solution to deal with this problem, I mean, in ROSPlan, we have done it in the past with MongoDB, with a database that just makes this relation. But then later on, we decided to simplify this and to remove also this dependency. and we decided to go more in favor with the parameter server. So the parameter server is a dictionary that is available in ROS, and here you can store those symbols. And in fact, the Turtlebot demo is exactly what it's doing. It's just storing the symbolic poses. So WP1, WP2, so the waypoints, as a string in the parameter server. And when you query this information from the parameter server, as a response, you get the pose. But this will be like an extremely simple environment representation node or component or way to do this. But of course, this can go very, very complex. And at DFKI, what we use is a software called Semper that is actually storing this information in an ontology. And then if you store this information in an ontology, then you can make reasoning. And then there are multiple ways of doing reasoning. So there's a spatial reasoning, there is geometrical reasoning, and so on. And yeah, so just to make you aware that this environment representation can go really, really complex.
So another question. Giorgio asked a great question. Is there a rule of thumb to decide which actions should be put into the state machine or which ones should be fed to the planner? Where do you define the line between planning domain and implementation of actions? Enjoy.
Yeah. Thank you. Yeah. I would say there is not a rule of thumb. I mean, I would say this is more like it's completely subjective, and it depends to the designer. This is a design choice, I think, and it depends on your robot. It depends on the actions that are available in your robot. It depends on how good your planner is. So, for instance, if you have like a very bad planner that takes a lot of time to produce a solution, then of course you need to make the domain as simple as possible so that your planner produces a fast solution, right? But if you have like a super awesome planner that is very quick, maybe you can ask more out of it. And this means that you can model a larger number of actions in your domain and have less state machines on the robot side. But I would say, in my opinion, if there is a sequence of actions that they are never going to change in order, and the order will be always the same, in my opinion, it does not make sense to put it in the planning model. So just offload this to some state machine implementation and abstract all of this set of actions into a high-level action, put it in your model and continue. The problem with that is that a few months from now, let's say 6 months from now, you have a new project coming, and this new project has different features, and you want to reuse the domain that you have used before. So for reusability, this is actually bad, because maybe you need a finer set of actions that will allow you to model some features of this new domain that you have not previously thought of. So in my opinion, you have like a base domain that you make for a robot, and this domain will slightly change over time, and it will create, it will sometimes go more abstract, and it will sometimes go more specific, depending on your problem.
Saman asks a question about the planner handling delays in between actions, for example, hardware or software delays.
Sorry, I did not fully understand the question. What was the question, sorry?
So, sorry, the question is, does the planner handle delays in between actions, in or between actions, due to hardware and software?
Ah, right, yeah. Yeah, I mean the sterile, yes. So you have an action duration, and this action duration coming from the planner is it can be deterministic. You can say this particular action will take 10 seconds to complete, and there is no room for failure there. This could be the case, and if this is the case, and you have executor which is not smart, then if the action takes 9.8 seconds, then you fail. So Steril is smart about this, and it can handle these variations. So even if the action takes less time to complete, it will get this feedback and it would react accordingly. So from that perspective, it sort of fixes some of the weaknesses of the planners. Like I said before, one weakness that the planner could have is that the planner could produce sequential execution, and Steril will be smart about it, and it will dispatch concurrently. And the second one is that it will handle this action duration with in a flexible way, in a smart way.